The way, it's my pleasure to introduce our first speaker of the day, Professor Ming Yi from Rice. Today, she's going to be giving us a talk called Flat Bands and Quantum Materials. So please join me in welcoming Professor Yi.
Thank you very much, Christina. And thank you all very much for waking up early. So it's really my privilege to be here. This is my first time here, and I'm really thankful for the organizers for giving me this opportunity to come here and learn with all of you. So as you notice, what I'm going to talk about is a bit different than what you've been hearing all week in that I'm going to tell you a little bit about our work in exploring flat bands in bulk quantum materials. So I think the strategy in which we look for flat bands is a little bit different, but I hope to basically use this as a progress report to tell you about what's happening in bulk materials and what we have found in those materials. So, wait, sorry, here. Oh, sorry, let me reshare. I think what happened? Yeah, sorry, I apologize. Let me try to reshare. I think this. Okay. Okay, good. Sorry, sorry about that. Okay, so as I was saying, so you've heard all week, I don't have to motivate why flat bands are interesting, and we also all know how we get flat bands, namely there are two energy scales. There's the Coulomb interaction U, and also there's the bandwidth W. So then obviously there are two ways to approach this. It's very nicely summarized in this paper by Andre Bernowick and also Nicola Renaud, which is that there are two limits to this. One is you can crank up the Coulomb interaction U, and what you will get are these atomically localized wave functions where they're not overlapping between sites. Or you can go to the other limit of crunching down W. And as I will show you, you can do this by effectively quenching the hopping, utilizing the destructive interference of the electronic wave function from interesting lattices. What I want to emphasize also is that even though you get flat bands in both cases, they are very different objects. And we can study these objects using spectroscopy. And so for most of what I'm going to tell you about, are results measured by this technique of angle resolved photoemission spectroscopy, or ARPES. I know when I was a graduate student, it used to be that it was mandatory to show a slide of this when you're talking about ARPES results, but it seems like nowadays a lot of people are very familiar with this technique, but since this is a summer school, please allow me to introduce the technique just for completeness. Okay, so ARPES basically operates from the photoelectric effect. We shoot photons at a sample, sitting in ultra high vacuum, and the photons will give enough energies to the electrons to come out of the sample. And then these photoelectrons are then captured by this electron analyzer, which then measures the energy and also the momentum, which is via the direction of the photoelectrons from the sample. And using the conservation laws of this photoemission process, we can back out these energy versus momentum relationship of the electronic states from which these electrons were ejected, right? So you can think about this effectively oftentimes as a way to directly map the electronic structure. So these are some of the data cuts, and then from these energy versus momentum cuts, then you can construct the entire 3D cube of these electronic structures, and from that manage to get constant energy contours or mappings of the Fermi surface. But I also want to emphasize that ARPES is not just a tool for mapping simply the electronic structure. There's more to it. So what we're really measuring is this single particle spectral function, AK of omega. And in this AK of omega, of course, it contains the bare band dispersions, which is the electronic structure, but also, very importantly, any kind of interactions or many-body effects that leave fingerprints that affect the single particle spectral function that the electrons feel in the crystal will also be manifested in what we measure. So a way to see that is that there's this term, which is the self-energy. And the self-energy is essentially the term that captures the effects of electron correlations. So if you're a person like me, you want to sort of see what this actually pictorially mean. So let me illustrate this a little bit. You can imagine if you have a non-interacting electron system, you get a bunch of delta functions. Each one has a 0 line width. So this is what you would see. And if you start to consider the effect of interactions, such as what you would get from a Fermi liquid system, this AK of omega can be rewritten into two terms. There's an incoherent part, which gets pushed to higher binding energy. And then there is still a relatively sharp peaks. These are the quasi-particles. And you can see that they're sort of mimicking the non-interacting limits, but with some modifications, right? So the modification can, to the zeroth order, can be grouped into this coherence factor Z, and it affects the spectra that we see in two ways. One is that there's an overall reduction of the spectral weight, so the peak area will be shorter than the non-interacting limit. And then the second effect is that it comes into this term here and modifies the electronic band dispersions also by the same factor. So there is a squeezing of the band in the energy direction, and that's another manifestation of correlation effects that we can directly measure. So how do we do this quantitatively? You can imagine if you're measuring a material which is moderately correlated, such as this iron nictide superconductor, oftentimes you see many bands, and you can slap the LDA calculations on it. And for moderately correlated systems, you will find that there is some agreement, but you can make a better agreement if you normalize the LDA by a factor. And that factor here is essentially a quantitative way of gauging how strongly correlated a system is. So this is how we can utilize RPS spectra to sort of look at correlation effects in the material. And of course, you can imagine for a system that is multi-orbital, multi-band, we can gauge these factors in a orbital-dependent, momentum-dependent, band-dependent way, and therefore gain more insight into the system. Okay, so that's my sort of intro of RPS technique. So coming back to this picture, then you can see that these two ways of getting flat bands, therefore, will have very different spectral properties based on what I discussed previously. So let me show you some examples. Let's first look at the left-hand side, the type of flat bands you would get by cranking up U. And as very well-known example of this are the heavy fermion systems. As in the heavy fermion system, we know there are these localized F electrons, these arrows. And when they're not interacting with the conduction electrons, then you actually don't see them, even though they actually have a exactly flat band, but they contribute no quasi-particle spectral weight, so you won't actually see them. You will just see the dispersive state and the small Fermi surface. And when you turn on interactions like Condensed interactions here between the localized electrons and the conduction electrons, then you can start to see the presence of these so-called, I guess, flat bands via the hybridization of the flat band with the dispersive states, right? So you can start to see them, and that's the only way in which we can actually see these from a spectroscopy perspective. Okay, so maybe another milder version of this is something that I study as a graduate student, and that is in these iron-based superconductors. And very interesting, these materials exhibit what we call orbital selective correlations, and you can directly see this in these RPS data. So essentially, these iron-based superconductors are multi-orbital systems, and near the chemical potential, all the 5 iron 3D orbitals are active, and so you see a bunch of bands at the Fermi level. And what I'm showing you here are data taken on this iron tricotinite system. So iron, selenium, and then you can swap selenium in for tellurium, and that's what we get from the different compounds here, shown here. Each one has a different amount of selenium in place for tellurium. And so essentially, I hope you can see that there are 3 hole-like bands here, and visibly this one, actually its curvature, which is inversely proportional to the effective mass, changes as you go from one end to the other, while the other ones are basically not changing very much, right? So already you can see here that in this multi-orbital system, this band becomes increasingly flat, and you can actually extract the effective mass for that band, which is shown here as a function of x, and you can see there's a divergent mass enhancement for that band. So this is sort of, I think, a visualization of that band becoming Mott localized. And you can capture that theoretically in this calculation done by my colleague Jim Xi's group. So they calculated two ends. One is you can see that all this purple stuff are dispersive states, and then you have a very much renormalized XY band shown here. And you can see its presence in a weak spectral weight and also in the hybridization it has with the dispersive states. And then when it becomes Mott localized, it's completely flat. And then you also don't see it because the hybridization is also turned off, right? So I think this gives a good visualization of what we expect for flat bands generated from cranking up U. So namely, as it gets flatter, there's a diminishing spectral weight, there's a diminishing hybridization with dispersive states, and naturally these are normalized against the Fermi level, right? And then so interestingly also, this is also a way you can actually see a complete reconstruction of the Fermi surface without any symmetry breaking orders because of a localization of a certain orbital. And that's actually seen experimentally using ARPIS as well. So I think this is an interesting example. Okay, so that's the left-hand side. Now let's contrast this with the right-hand side. What would happen if you have flat bands, which is produced by reducing the kinetic energy W? Okay, so the most well-known example in the past couple of years is this Kagome system. I'm sure everybody knows about. So these are lattices which are made of corner-sharing triangles. And the way that kinetic energy is quenched is because of the destructive interference of the electronic wave functions. So you can see these two sides. There's no hopping out at the side that they cancel. So so there's no hopping across these hexagon plaquettes. And therefore, in the momentum space, this will give you a flat band. And this flat band also for a Kagome system has two dispersive states that they're touching with this flat band. So the poster child for a Kagome lattice arguably is cobalt-tin. This is really nice work done by the MIT group, Dorchakowski and also Ricardo Komin. So they see that here in the cobalt-tin, where the Kagome lattice is from the cobalt lattice, these bands, which nicely match those of the DFT, originate from these flat bands, as you can calculate from the tight bending calculation, right? So you can see that in contrast, the previous examples that shows you, these flat bands have full coherent spectral weight. They're touching with the dispersive states, and also, of course, where they are in energy is completely dependent on fitting, right? So these are some of the differences with the correlation-driven flat bands. So here I just lay out as a little summary of the differences between the two cases. In spite of the differences, I think theoretically we still recognize there's a lot of similarities between the two cases, and there's been a lot of theoretical treatments on proposals on how to map one onto the other. I just show you two examples. There are others. I apologize, I'm not showing everything, but here are two examples. This is the very nice model, topological heavy fermion model proposed by Andre's group, and where you can see essentially you have a flat band and also dispersive states, and this can be mapped to a heavy fermion model. This is the other construct from Jim Xi's group, where they are grouping the topological flat band together with a dispersive state that it touches, and grouping this whole thing as a single object, which they call the compact molecular orbital. And then taking this as a single object, then they can apply what they have already built on the heavy fermion systems to linearize this. So in recognition of the similarities, I think it's interesting that we can, from a spectroscopy perspective, look at systems that exhibits one or the other, or exhibits the different types of flat bands, and then look at how they can participate in immersion phenomena in these materials. So that's my big intro, and then for the rest of my talk, I'm decided to do this in two parts. I'm going to spend the first half of the rest of the time talking about different lattices that our group has encountered where they gave rise to topological flat bands. These are three constructs, and go through them one by one. And then for the second half, I would like to also discuss some of the more recent results of specific systems, bulk materials, where we have found flat bands near the Fermi level, And I'm going to show you what we can interpret as a role of these flat bands towards producing magnetism. So these are the 6 topics I'm going to go through one by one. So I hope this is interesting to you. Okay, so let's first do the first half. I already talked about Kagome a little bit, but as we know, there's a vast database for bulk crystals, and there's been really nice cataloging work that looks through the many different crystal structures that we already have, and look for lattice motifs that would give you this kind of geometric frustration. This is a very nice work from Joe Chakowski's group, where they pull through compounds and materials project and look for these most commonly occurring lattice motifs that will give you, this is on tight binding calculation, flat bands in these structures, right? These are the top 5 contenders that are that are occurring. And then of course, there's this very nice catalog paper that actually looks at specific compounds that exhibits subunits that would give rise to relatively narrow bands near the chemical potential, right? So there are a lot of materials that we can actually study already based on what nature has already given us. So let me talk about a little bit more about the Kagome lattice. It is special not only because of flat band, but there are total three key signatures in the electronic structure that people have theoretically connected to emergent properties. So this is one cut. This is the complete 3D electronic structure from the tight binding. So you can imagine if you put your chemical potential to be in the flat band, as we heard all week, then you can naively expect there should be some sort of stoner itinerant ferromagnetic order. Then there's also a Dirac cone that appears, that's guaranteed to appear at the K point in the Brillouin zone. And then if you include the orbital coupling, this will give rise to Berry curvature and almost Hall. And then the last set is a set of Van Hove singularities, or bands that are saddle points. And in the 2D limit, this will give you also divergent density of states. And this occurs, these Van Hove singularities occur at a very specific point in momentum space, and such that if you tune your chemical potential to be there, then you will get this idealized Fermi surface, which is hexagonal. And you can imagine you can see that there's these 3 pairs of Fermi surface sheets that will give you a nesting vector, wave vector. And theoretically, this has been connected to the emergence of a charge density wave, right? So Kagome lattices are interesting. And in the past couple of years, there's been a lot of study, a lot of activities in the community looking at all kinds of Kagome lattices. This is not a complete list, but this is my way of sort of demonstrating what kind of emergent phenomena have been discovered in Kagome lattices. Largely, there's superconductivity. The people have observed charge density wave and also magnetic water. I've also highlighted in these compounds the element that actually forms the Kagome lattice. And you can see that these are all transition metals here. And all of these have been discovered and studied in these form. And so if you actually zoom out and look at the band dispersions calculated by DFT for various numbers, you see that there are certain patterns. And if you're a person who does not enjoy looking at spaghetti plots that much, I try to highlight what's important to read out from these plots. And you can see the tight binding signatures in the spaghetti plots. I hope you can see that. And here are the Fermi level for each one. And I think you can already see that here in this corner are the iron and manganese-based Kagome lattices. And this calculation, which is calculated from the non-watered phase, has the flat band right at the Fermi level. And so coincidentally, these are also the systems with magnetic water. Going up here, these are the vanadium-based Kagome lattices. And here you can see that the flat band is above the Fermi level, and it just happens to be that the Van Hove singularities are near the Fermi level. And And there are a lot of discussions about the discovery of charged density wave waters in these systems. And then this, I just want to highlight this last member, which was discovered last year. And this is the chromium-based Kagome lattice. And here it is, chromium is in between. And you can see that the flat bands are actually closer to the Fermi level. And this is the most interesting one, perhaps, because in this compound and in this phase diagram, people have found superconductivity, charge density wave, and also magnetism. So I hope I have time towards the end of the talk to talk a little bit about what we have found from this compound in the end. So this is my way of sort of showing that there's a lot of phenomenology, interesting physics, which we can tune by tuning across these transition metal elements. And not only does this tune the chemical potential, but also this is a way to tune the electron correlations in these compounds as well. So I'm going to touch upon that a little bit as well later. So this is sort of introduction of what's happening in the Kagome lattice field. Okay, so that's in 2D. Next, I want to discuss a little bit by going one dimension higher and talk about the 3D pirate core, which is the second most common lattice motif in bulk materials. Okay, so as we know from quantum spin liquids, a pirate core lattice is something like a 3D version of a Kagome lattice. This is also a geometrically frustrated lattice. You can see this because if you cut through, these are corner sharing tetrahedron. If you cut through along the 1-1-1 direction, you can see the Kagome planes here highlighted in this bold black things, right? And there are 3 ways to cut this. Here I'm showing you 2 ways of cutting this. So it turns out that if you calculate the linear amplitude, the 4 sites within one of these tetrahedron, 3 are contained in the plane, and there's 1 which is not contained in the plane. It turns out the one that's not contained in the plane has 0 amplitude. So this suggests there's no hopping across the layers for pirate core lattice. And so essentially then we can understand this 3 pirate core band structure as effectively 2 decoupled Kagome planes, and everything we know about Kagome actually carries over, except now in the tight binding we have 2 copies of the flat bands in addition to 2 dispersive states. So this is the tight binding basic electronic structure of a pirate core metal. And the interesting features I sort of point out at you, there are 3 bands that meet here. This is the triple degeneracy point. And then there are like a nodal line between certain path in the momentum in the baryon zone. So if we include spin orbit coupling, here is what happens. There's a gap that happens between these 3 bands. You end up with a double degeneracy point at the gamma point. And furthermore, what's interesting is that in the presence of SOC, you still have, for every single band crossing that crosses the X point is here, it is a gapless 3D direct point. And the reason for this is that this crystal structure has an inherent non-symmorphic symmetry. And how do you see that? Pictorially, you can sort of see this by, if you pick out the site, which is contained within the tetrahedron of the pirate core lattice, those sites forms a diamond lattice. And the diamond lattice has been very well known. There's a screw axis here. And the screw axis is composed of an in-plane 4-fold rotation with a quarter translation. And this non-symmorphic symmetry, it maps back to the pirate core lattice, is what guarantees that every band crossing here is gapless. It's a gapless 3D direct point. So those are the 2 takeaways for the key signatures in the pirate core. You have flat bands, which are bands that are flat in all 3 directions, Kx, Ky, and Kz. And then also you should see that every pirate core should have 3D direct points at the X point. Okay, so that's the sort of like just our understanding of this. So let's look at real material. What do we see? So the first compound that contains a pirate core lattice that we have encountered is this is a serum ruthenium-2 material, and this compound belongs to a large family of lavas phase, and this is their crystal structure. And I just want to give credit to Condensed, who was a theory postdoc from Chimel's group who first told us about this pirate core lattice, and then Jianwei Huang is my really excellent postdoc who did the ARPAS work on this compound. So if you look at this crystal structure, the ruthenium sublattice, you kick out the cerium, the ruthenium sublattice forms a pyrophore. So we started to look at, how much of this flat band business is actually there for this material. So Jonathan Dunninger helped us do some calculations. And so first, we start with the ruthenium pyrophore. So we take off all of the cerium, and this is what you would see for just a pure ruthenium sublattice. These are the pyrophore flat bands here. And we can slowly approach back to cerium-2 and see where these things evolve. So the next step is we added in lanthanum in place of cerium because they have no F electrons, right? So then you can see that these are the bands which are evolving from the original flat bands of the pyrophore lattice. And then you eventually add cerium, and these are the bands that we can trace out that are originating from the original destructive interference-induced flat bands. And there are still portions of flat bands near the gamma point, but there's sufficient hybridization also with the rest of stuff, so which makes it less flat, but we can still find traces of this. And I remember there was a question 2 days ago about whether you can cleave cubic crystals. For some crystals, you can. So if you try hard enough, you can. So this is what Dewey did. He cleaved a bunch of crystals, and you can eventually actually get pretty good band dispersions out of these cubic crystals. So you can see there are portions of flat bands around the gamma point, and this is originating from the pyrophore sublattice, as well as direct crossings of the X point and the boron zone. So we can see the two main takeaways from the pyrophore lattice. But we weren't exactly happy with the fact that some of the flat bands were hybridized away with the rest of the other atomic sites. So we want to find better materials that can better preserve pyrophore physics. So we went and looked for another material, and this is a spin-out compound, copper, vanadium 2, sulfur 4, and there are a lot of sites. But it turns out that the vanadium site here actually is a pyrophore sublattice. And what's really nice about this material is something that Joey realized is that if you look at the copper sites, all of this unit, this tetrahedron with the copper and the sulfur are fully occupied, which means that they should not contribute any stuff near the Fermi level electronic states. And it's the vanadium sites, the vanadium is the vanadium from the pyrophore lattice, that are partially filled. So this is very promising because then this suggests that the dominant low energy physics is likely associated mostly from the pyrophore sublattice. And that's indeed true. So from the DFT calculation, you can see that the density of states here, all of the stuff within 1 eV of the Fermi level is all blue, and that's vanadium. So the copper and sulfur are farther away. So that's good news, which means that the vanadium sublattice is not so much hybridized with other stuff. And you can indeed see this extremely flat band here, which is all vanadium T2G. And it's relatively untouched by the other stuff. So that's great. So we went and did ARPAS measurements on this, and he could actually see an extremely flat, fully coherent band near the Fermi level. This is the spectral image. If you don't like reading images, these are the line cuts, which are basically vertical energy distribution curves. And you can see these sharp peaks all hugging at the Fermi level, which is actually very promising. However, if you come back to DFT, if I went slow enough, you will notice that this flat band or density, this high density of states associated with the pyrophore flat band is actually half eV above the Fermi level according to DFT. But why do we see this actually at the Fermi level? So then we went and looked at his dispersions, and if you zoom out to a large energy scale, what he realized is that, so this is the data, what he realized is that this is just DFT overlapped. The band dispersions, the electronic states we see farther away from the Fermi level actually agree with DFT quite well. So those are mostly the copper and the sulfur states. It is the stuff which is near the Fermi level which do not agree with DFT very well. And those are the vanadium T2G states. So this is very reminiscent of what we found previously in the iron tricotonides, that for a multi-orbital system, you may have correlation effects, which depends on which orbital you have. So with that thought, then we reach out to Chimel's group, or and try to study this. So how do we incorporate correlation effects to make a better match with our observations? So what they did is Leighton did a tight binding fit to the vanadium T2G states near the Fermi level, and then added put this through a state spin calculation, and then by incorporating Coulomb interactions U, they can renormalize states down to the Fermi level, which actually has a much better agreement with our measurement, not only for the flat band, but also for the dispersive states. You can see here are much better agreement than the Bayer DFT that we had previously. Okay, so what does this tell us? In our simple mind, this tells us that actually two effects are in play. First of all, we have topological flat bands from the destructive interference of the pyrocore sublattice that creates the topological flat bands. In addition to that, there's also moderate electron correlations that further normalize these flat bands to the Fermi level, and eventually both these two coming hand in hand in producing this flat band at the Fermi level. And as a result, we also see some non-Fermi liquid transport behavior. This is the fitting of the power law exponent of the transport as a function of temperature. And so this is the case where we can see some reminiscence of the correlation effects together with this topological flat band construct from the pyrocore sublattice. So I thought this is an interesting view of how we can look for flat bands in 3D. Okay, now I come to the last example. I think this one is very different from the previous two. And I also want to tell you about this way, yet another way of perhaps looking for flat bands in bulk materials. And the thought is that the key tuning knob here, or the key role here, is a role which is played by a vacancy that could order in a bulk material. So what I mean by that, so here I'm showing you on the left-hand side is this triangular lattice, or it's essentially honeycomb lattice, but with two species. They have a yellow site and then the red site. And if you now imagine puncturing out holes in this lattice or creating vacancies and do that in an orderly fashion, you may see that you can create some sort of a superlattice like this. So this is empty site, full, filled, empty. And what you can see is that this particular lattice actually is very interesting. It's a repeating unit of such a shape, which my student would call the clover lattice, but I think I realized this is very similar to the fidget spinner that Una discussed earlier as well. And what's special about this is that this is a unit that contains, this is a bipartite lattice because the nearest neighbor hopping is always between species of different sublattices. And the number of sites for the red sublattice is 2 per unit, and then for the yellow one is 3. And because these are different, you're actually guaranteed to have a topological flat band here. Another way to see this is that there's also a destructive interference of the wave function here, such that you cannot have hopping out of these plaquettes if you only consider nearest neighbor hopping. So this turns out to be a very special lattice, and if you can include spin coupling, then this becomes a topological. It has a term band. Okay. So why am I telling you this? The reason is, of course, we found this in the real material, and that material is none other than this 2D van der Waals ferromagnet, iron, germanium, tellurium, which was discovered a couple years ago. This is a large family of exfoliable van der Waals ferromagnet, where it's been found to retain long-range magnetic order even when you exfoliate down to monolayer. But the key one I want to focus on is this last number, so iron 5, germanium, tellurium 2, and not only because it has the highest Curie temperature near room temperature, but also it has this special vacancy that actually can be utilized to form this order to give you this clover lattice. So let me go a little bit more in detail on how we see that. So this is the unit cell, has many sites. This is a TEM cross-sectional view. essentially you can pick this thing apart. This is just ABC stacking of van der Waals slabs. And if you focus on one of these slabs, I zoom it out a little bit here, you can see them. I'll tell you that it's an inversion symmetric crystal structure where the inversion center is between these two blue sites here. This is split germanium sites, but don't worry about it. So everything comes in pairs across this. You have the tellurium here on the outermost layer. Then you got two pairs of iron 2, iron 3, which are inversion symmetric. These are all fully occupied as far as we know. And then the most important one is the last pair, this iron 1 sites, there's up one and down one. And if you have exactly iron 5, 1, 2, then between every up-down pair, only one of these can be occupied. So the crystal's got to choose which one to occupy for every up-down pair. And it turns out that the crystal it can be stable in two forms, and this is where the water one comes into play. It can have a stable phase where whether it chooses the up one or the down one is completely uncorrelated as you go across the crystal. So essentially, we can consider each of these sites as on average 50% occupied. And you can see that for this, the global inversion symmetry is actually preserved. Or the crystal can find a stable structure where it chooses to occupy the site in a correlated fashion. So it occupies the up, down, down pattern, and so on and so forth. So inversion symmetry is broken, and this also becomes, right, like there's a superlattice associated with this. And the reason I'm telling you this is because this is precisely what actually gave rise to the structure I motivated this thing with. So this is a cross-sectional view, but if you look into the plane, these are the shorter spawn layers. If you look into the plane, this is precisely what gives rise to this contrasting thing. And this ordered phase is the one that actually gives you this √3 by √3 iron 1 site ordered phase, this repeating clover shape. So all of that motivation is just to say that we did photo emission on this, and we actually indeed see flat bands in the ordered phase. You can see there are these flat features. Here is energy versus momentum, 5 cuts across the Brillouin zone, and you can see these pervasive flat bands across the Brillouin zone associated with the site ordered phase. And they're not there. We mapped the situation where this clover lattice destructive interference is turned off, right? So this is our interpretation that these flat bands are indeed associated with the presence of these clover lattice. So this is yet another way to create flat bands is by considering systems which may have vacancies that order, and then that could potentially give you new symmetries or new superstructures that could potentially carry this potential to create flat bands. Okay, so that's my intro for the first half. I want to then take the rest of the time to go on to the second part, which is given the flat bands that we have found in various systems, how do we see, what do they do? And I'm going to try to show you some of our results and our interpretation of our results from three bulk systems where flat bands have been found near the Fermi level, and they also have emergent orders in them as well. So, so that's the next part. Okay. So as we have learned that these flat bands in real space are these compact localized states, and they are indeed been imaged. So this is a very nice STM work that shows that if you tune, this is the STS map, and if you look at the binding energy, this is Kagome cobalt tin. If you look at the map at the binding energy where there are expected topological flat bands, they actually see precisely these compact localized states in the center of these hexagons. And if they tune the energy away into dispersive states, this changes to the actual atomic sites. So these are real objects, and these objects potentially could act like local moments, and they could generate theoretically generate phase diagrams that mimics what's known about heavy fermion systems. So then we want to think about what do these objects do in terms of creating emergent phases. To address this, before I address that, I want to just show you, I guess for the younger audience, how we may think about probing the nature of ferromagnetic order from spectroscopy. So as we know that when you think about ferromagnetic order, there are two extreme ways of understanding magnetic order. One is the Stoner model, and here, because of the high density of states, that will spontaneously break into spin up and split into spin up and spin down bands, and that's what gives you the overall magnetization. This is the itinerant model. There's on the other limit, we also have the Heisenberg model, where the magnetic order come from local moments, right? So, and here you also have the splitting of the spin up, spin down bands. This is the exchange splitting energy scale. So how do we distinguish these two cases? The way to distinguish them is by doing a temperature dependence, because for the Stoner model, what you would expect is that the spin splitting should merge exactly at the Curie temperature, because this is what gives rise to magnetization overall. In contrast, for this for the local moment picture, the local moments themselves actually still persist well above the ordering temperature. The ordering temperature is just where you have the overall correlation of the moments. So locally, you still have the up-down states, but macroscopically, the spin polarization of these bands will be washed out, right? So you can see that a direct way to look at to distinguish the two cases is by ramping the temperature across the ordering temperature and see whether the spin splitting actually disappears or how much actually disappears to distinguish these two cases. And this has been commonly used to look at the nature of magnetic order. For example, this is what's done on iron film, which is many people consider to be itinerant, but even for iron film, the white squares is a measurement of the spin polarization of the band, and the blue dots is a measure of the splitting of the two bands. So what you see is that this is the actual ordering temperature where the spin polarization disappears, but even for this iron film, the exchange splitting actually still persists well above the ordering temperature. So you can see that there's already a degree of local moment in play here in this measurement. So we can actually look at this kind of measurement to sort of get a sense of what is the degree of local moment versus itinerant magnetism in these materials. So we tested it out. The first one we tried is iron tin. Iron tin structurally is probably one of the simplest Kagome lattice materials in bulk. And it's made of these sheets. Iron is the one that forms the Kagome lattice. And then it orders at 366 Kelvin. And the magnetic order is A-type, AFM. So each layer is ferromagnetic. And then they're anti-aligned in the z-axis, right? So in single crystal form, this has been studied by various groups. And I guess the question is, we want to ask, what is the role of the flat band in this magnetic order? So to address this, my postdoc, Zheng Ren, came to our group 2 years ago to build an MBE system, which is connected to the ARPIS system. And then they could, that would enable him to grow these Kagome films and then directly transfer to the ARPIS chamber to measure. So to our pleasant surprise, it turns out that these films are very robust. Unlike the single crystals, which you cleave and they don't live very long in the chamber, these films turns out to be very robust. You can thermal cycle them to high temperature while across the ordering temperature and then cool back down. All the features are still there. So this actually gives us the first chance to actually look at the nature of magnetic order in these iron tin films. So that's what they did. So to make a long story short, let's first look at what we actually expect theoretically, right? Why we can, this is A-type AFM, how do we map this to this kind of picture? It turns out that we can consider each of these layers as ferromagnetic, and when they become ordered, then we can expect that to be a spin splitting of the spin majority and spin minority bands. And this is what you actually see from the spaghetti plots, which is calculated by Binghai Yan's group. For the non-magnetic phase, I showed this in the earlier slide, you see a big peak in the density of states at the Fermi level. Those are the Kagome flat bands. And in the AFM order phase, you indeed see this split into two, and which map to the spin minority and spin majority Kagome flat bands, right? So So in essence, then therefore, this gives us confidence that we can look at this by examining whether these bands close or not across the ordering temperature. Okay, so first, in the base temperature, lowest temperature that we can measure, we do see peaks in the density states around 1.2 eV, but below the Fermi level, which actually agrees very well with relatively well with the spin majority Kagome flat bands predicted by DFT. So that gives us confidence that we can, take this energy scale as experimentally. This energy scale is likely a good estimate of the actual energy scale. So next, we want to do is to ramp the temperature across the ordering temperature. And we can find pieces of the band which belong to the spin majority states. And as a function of temperature, they indeed move up as expected. And then we can find pieces of the band that belong to the spin minority states, and they indeed move down as you ramp up temperature. This is energy. However, if you read off the scale, or you cannot read off the scale, but I put it here, the total amount of magnitude that these bands shift is a very small portion compared to the total exchange splitting energy scale predicted by DFT. Right, so what it's telling us is that by the ordering temperature, only a very small portion of the exchange splitting actually is closed. So this is actually very direct evidence that what we're seeing here is not itinerant mechanism, but really much closer to the local moment side of the picture for the situation where the flat band is at the Fermi level. That's the first case. Now I want to show you a contrasting case. This is a very different side of the story. So coming back to this site-ordered phase-induced flat band here in iron, germanium, tellurium, I've showed you these evidence for these flat bands associated with these Clover lattice. We can now look at what happens as we crank temperature. So the way to see this is we take a cut, say along the high symmetry direction, which is shown here, energy versus momentum, and we find a region in momentum space here that has a clear view of where the flat bands are. So we take these energy distribution curves. So at the lowest temperature, you see bump, bump. Those are the flat bands. And then as you ramp up temperature, you see these bumps actually merge together. We also carried out spin resolve RPS measurements, and we can actually see, very interestingly, that these two flat bands have the opposite spin polarization. So this is suggesting to us that in this situation, we actually see this case where we have a flat band near the Fermi level that becomes spin split as you enter this below TC. So this is a very contrasting behavior than the iron tin situation I told you earlier, right? So even though they both have flat bands near Fermi level, but they could have very different origins. Sorry, okay. The last bit, I want to show you the last example, which I think is actually a very interesting material, which is a lot of progress has been ongoing for this material, which may be the even more interesting one. So to introduce this compound, chromium is the Kagome lattice. This was discovered last year. I think the paper is coming out in Nature soon. And what they find is that they can actually map out a phase diagram for this compound that looks very much like what we have seen for the cuprates, pnictides, heavy fermi, and so on and so forth. And the horizontal tuning axis is hydrostatic pressure in this case. So what they see is that at zero pressure, the parent compound exhibits a temperature scale of 55 Kelvin, where they see superlattice peaks popping up, which suggests there's a charge density wave water. And they also see a shift in the NMR signal, as well as kinks in the susceptibility. So this suggests that there are actually two transitions, and as a function of pressure, these two transitions actually become separated and very quickly suppressed by pressure, and then eventually they see the emergence of superconductivity here in this dome-like shape. And in addition, the color on this phase diagram is the power law is the power of the transport, and so you can see that this is largely a fermi-liquid regime, exponent close to 2, and then this is mapping out to be what they label as a non-fermi-liquid regime. And this seemed to be very suggestive of phase diagrams that we have seen before. So this is like a very, very interesting compound by this analogy. So we were able to get some crystals from my colleague Condensed group, and we wanted to take a look at where the flat bands sit in this material, whether that has any role to the emergent orders. So this is, again, let me do this again. So this is the plot that I showed you in the earlier slides. This is the chromium sample. This is the vanadium version. The vanadium one, remember, is the one with the well-known CW order. Even with DFT, the flat bands are much closer to the Fermi level, as you can see in the density states. And when we did measurements with photon emission, we can actually indeed see clear signatures of the flat band. If we zoom in here, if you don't trust the images, let's look at the EDCs. You can see really a flat feature hugging the Fermi level here, which suggests the flat band is actually lower than what's even predicted by DFT, closer to the Fermi level than what's suggested by DFT. Another way to see this is by zooming in around the gamma point. So the gamma point has this electron band. And here, you can actually see some spectral weight here, suggested by this peak. And that's because of the hybridization of this electron band with the flat band. And in contrast, for the vanadium case, because this is much higher, you don't see anything here. And so this is another evidence that the flat band is actually observable at the Fermi level. So as a function of temperature, we track the position of the flat band, and we can see that as it enters the ordered phases, it actually shifts away from the Fermi level. And so just as a very hand-waving interpretation, we can think about what actually would happen when this density wave gets suppressed. Perhaps that leaves the larger residual density states near the Fermi level, and then eventually that actually it's connected with the superconductivity. So this will be very interesting to further study this phase diagram by finding other tuning knobs besides pressure that can allow us to directly access the superconducting dome to see whether this in bulk materials, these flat bands, can actually be associated with the superconducting phase. So I think this is a very interesting direction as well. I think I've gone a little bit too long. So this is just to summarize. I showed you the two sections and some ways of thinking about. I know in 3D bulk materials we've heard a lot. There's a tuning knob is not as nice as in 2D materials, but still we can sort of try to summarize some of the insights we have gained by looking at the vast types of different bulk materials. So we can think about creating topological flat bands in bulk by starting with geometric frustrated lattices that form as sublattices in bulk materials. We can find systems, and the next step is to find systems where these flat bands are not heavily hybridized with other trivial bands, as I've shown you in the case of the spinel copper vanadium sulfur case. And then we can also think about systems where you have partially filled 3D states that could perhaps give you additional Coulomb interactions that can further renormalize the flat bands towards the Fermi level. And then we should think about exploring other things like vacancy ordering that can give you additional ways to create topological flat bands not captured currently in these databases. So in the end, I've tried to motivate that in 3D bulk materials, we have various tuning knobs. We have dimensionality, we have vacancy order, we have this degree of sublattice coupling, lattice distortion. And then we can also think about maybe not black-white picture, but perhaps in most materials, it's somewhere along the scale of both correlation effects also together with geometric frustration. And eventually, hopefully, this gives us a way to a large phase space to explore different phenomenologies. So that's the sort of the summary. And then I just want to acknowledge this is my group for the various members who work on the things I talk about. Jianwei Huang is a postdoc who works on the pirate core systems. Han Wu is a student who just graduated who worked on 2D magnets. And then Zheng Ren is the MBE guru. Yucheng Guo is the one that works on the recent chromium-based samples. Jisoo Oh is also another postdoc who works on iron germanium, which I didn't have time to talk about. And then And just thank all of our collaborators, especially pointing out Qimao C's theory support, Peng Dai's group on many of the compounds, and then Junhao Chu's group on the 2D magnets, Ming Yi Yan's group on the DFT calculations, and then many of the beeline scientists we've worked with in North America. So thank you very much for your attention. Mm-hmm.
Hi, thank you for the talk. So I used to near your last slide, what was the sense in which your non-Fermi liquid phase was a non-Fermi liquid?
I'm sorry?
Oh, what is the precise sense in which the non-Fermi liquid part of your phase diagram is a non-Fermi liquid?
Which part? Sorry, I didn't hear.
Repeated.
The
Yeah, this one. Yeah, so that non-Fermi liquid phase, I guess why would we call it a non-Fermi liquid?
Why they call this a non-Fermi liquid? Oh, because the power law of the resistivity is somewhere between, like, it's close to linear T-linear behavior. That's the gauge by which they label this as a non-Fermi liquid. Yes. This is not our paper, but I just want to, that's sorry, this is not the right citation, but it's other, yeah. Yes.
Topological flat bands, but is there any evidence of topology in the experiment beyond theory?
That's a very good question. I don't have a good answer to this. For photo emission, we don't have. So this is another part where we are not yet at the regime where we can look at this like the 2D materials. We have to look at how to minimize crystal disorder. We have to lower temperature and then try to, and then look at separation of the flat bands from other dispersive states. So that's one point that's not so well. So topological at this moment is truly coming from just the origin of these flat bands from theory perspective. We don't yet have, yeah.
That is, it seems that the flat band you get, if it's come from vacancy, it's just some sort of quantum, the flat band probably is trivial.
So so if it's just from disorder or those kind of states, then you should not have any hybridization with dispersive states. It should just be a flat feature. So that we actually we actually do see this band hybridizing with other states. So for example, at least I guess it's not. So you can see, for example, on this cut, the flat band actually hybridizes with dispersive states where they meet. So we're pretty sure that's intrinsic band from this argument, at least. If it were just disorder, it should just be by itself. Yeah, that's a good question. Go on.
Some difference.
So I guess what I'm calling 2D is just for the Kagome system, the destructive interference is only there for the in-plane direction. When you stack them in the real bulk crystal, you always have interlayer coupling, which will deviate from the destructive interference in the 2D. So for the 3D pyrocore lattice, this destructive interference is there in all directions intrinsically. So I guess that's the only reason I call them 2D versus 3D. That's, yeah.
Oh yeah, just a naive question. Would you mind giving a rough idea why you use the slate for the interacting part of what you were doing before?
Because my colleagues is next door, so that's the only reason. But if anybody else is interested in like doing this with different methods, we'd be happy to talk or collaborate. It's just because Qimao, we've worked with him for a long time, and I don't have any. That's just experimentalist is well, but there's no deeper reason for this. Yeah, I know that works for the iron nictite case. So I guess in that case, in that sense, this is sort of analogous. Yeah. Yes.
Thank you for your talk. Ask a question about the physical picture about distinguishing the two paramagnetic mechanism. So in the Heisenberg picture, you claim like does that mean the local moment will not influence the band structure, the splitting?
So locally you still have locally you still have extreme splitting because locally you still have different spin-off states. So there is some energy. So you will still see the spin splitting, the bands. but they won't disappear if you go across order temperature because it's not all like correlated across the sample. So locally, you still have spin bands, but just overall, what's spin majority, what's spin minority is no longer meaningful. Therefore, you lose the spin polarization. But they would still, right, so, but you still have so for any side, you still have, the electrons still see the difference between being spin up versus spin down. Therefore, you still have the band splitting. Is that it?
The moment they coupled with the internal electrons, they form like a bound state. It's probably going to normalize the band.
Sure, this picture is very it's a very simplified picture, just considering, of course, you have other hybridizations, that kind of thing, but this picture is just meant to be simplified picture to distinguish the two scenarios. Yeah, I'm not saying this is for a real system. You should, of course, it'll affect other states, but this is just a schematic, I guess. Thank you. Yeah.
Kind of a follow-up on this. So in the paramagnetic state of the local moment, I guess I'm a little confused why they're split, because just as long as you don't apply field, I just feel like the spins are randomly oriented.
Yeah.
Why do they split?
Right, so if you do magnetization, you won't see any magnetization, because basically that's the same statement as saying the spin polarization is zero. But locally, because you still have the local moments, they're just not all aligned, you will still see a difference between spin up and spin down states, electronic states. So therefore, there's still energy difference between the two. But you don't, like if you measure magnetization, I think I guess what you're thinking is if you do magnetization, you won't actually see any signal in that phase unless you flip all the spins with the field. This is just, yeah.
Okay, if there's no more questions, let's thank Professor Yu again.